Okay, welcome back, my friends, to another episode of Uncertainty and Probability Theory, the Logic of Science. I'm William Briggs, and this is episode 35. And we've done quite a lot up to this point, but I still don't think a lot of people are getting it. So what I wanted to do is have kind of an overview course of everything we have done so far and a hint of what's going to come, and put it in the simplest possible way. I should have labeled this one even episode 0, sort of a pre-course. Now I'm going to go over everything, the absolute complete theory of the philosophy of probability, but I'm not going to prove anything. I'm just going to make statements. I'll say where and what we have proved so far, what proofs have yet to come, and give nothing more than that, okay? So I'll try not to use too many words. I'm going to show you what probability is, and I'm going to give you some prime examples, just a couple, 2-3 examples of what probability is not, and the importance of this course for changing practice. Okay, so here is all of probability is in the simplest possible way that I could say it. We start with something we want to know, and we want to think about whether or not it's true. So it could be the amount of rain, it could be whether or not you got a job if you had worn a tie to the interview, which you did not, a counterfactual. We could think of it as an answer to a user query in some artificial intelligence thing. What's the best next letter to print out? Or rather, what's the most probable in a sequence of letters or words or sentences that we can put out? Where an electron is, how much dark mass is here, whether or not somebody has cancer, where your wife is, whether or not Socrates is mortal, whatever. The proposition is up to us. This is something of interest. These are all very simple propositions, but they can be quite complex too. Multidimensional, all these kinds of things. It's something we want to know. Anything. And then we specify, and trying to put it in the simplest way I can, all evidence and assumptions, data, guesses, models, grammar, including the grammar of what all this stuff means. The amount of rain in a spot has a definition. And the grammar of each of the words we're using to define this stuff, mathematical or language grammar, all of that stuff matters. It all counts. Whether or not we have a model in this, yes, we have models, et cetera, et cetera, et cetera. Everything we have in here. Finally, and a lot of this stuff is not written out. The model part is normally, in science, the model part is formal. But a lot of this other stuff is informal. It's only tacitly or implicitly there. Most often the grammar and the definitions, which we just take for granted. And everything becomes the models. The models become reified. We have the deadly sin of reification. The deadly, I should have wrote this up here on the board. The deadly sin of reification is when the model becomes greater than reality, which happens all the time in science. You say it doesn't because no scientist would make that kind of a mistake, but it happens all the time. We rarely do this when we're thinking about questions of where the wife is, and I'll explain that example in particular. And in the end, every problem, without exception, every problem without exception has this form. We write it in this form right here. This is notation. Sometimes notation is helpful for us. Sometimes it's not. I think it is here. We read this as the relationship of y assuming x, or given x, or assuming x is true. It doesn't mean x is true, because we could have counterfactuals. We could have, this is another one we could have here, the number of unicorns that come out of a room. Unicorns that emerging from some process. There are no unicorns, but we could still think about unicorns. We could still think about uncertainty in counterfactuals, as we'll see. So this is a relation. That's all this is. That's all this means. This is the relation of y, assuming x is true. That's all it means. Now, this can be math. We proved that this can be put into mathematical form. From first principles, not starting like Kolmogorov does or something like this, but we proved using Cox's theorem, we proved that this can be put into a mathematical form. Can be. Doesn't have to be. Not everything is mathematical, as we'll see. And we proved the form that this math takes. Turns out to be Bayes' theorem. And then we proved the range, the numbers that this mathematical form can take, and that's the familiar 0, 1. So these are all very familiar things, but a lot of times when you take these probability courses and so forth, they jump right to here's the Kolmogorov axioms or some other similar axioms, and off we go to the races, understanding you're only taking a small branch of probability and not the entire thing. So we can't think about coincidences. We can't think about counterfactuals. We can't think about simple questions, the kind of stuff that we ask ourselves all of the time. Doesn't fit neatly into that mathematical framework. Although this framework here, which we now see means the probability that y is true, assuming x is. The probability y is true, assuming x is. Okay, it doesn't have to be a number. So let me erase some of this stuff, and I'll work through a couple of examples. I'm not going to work through anything. I'm just going to state them. I'm not going to make any proofs here, but I want you to follow this. So, for instance, I want to know where my wife is. Where is my wife? My wife is shopping. This may be one of the things I'm entertaining. My wife is shopping, and my evidence is today is Thursday. And on Thursdays usually goes shopping at this time. And I know what the implicit tacit premises are. I know what Thursday means. You know what Thursday means. If you're listening to this lecture, you know what shopping means. You know that this means the wife is not here if she's out shopping. And we form probability of y given x. And all we can do in this case is to say something like usually. There's no number we can assign to this unless we go back and add to this x. We add to this x some sort of map of usually to a number line. Or maybe that's the bad example. Maybe something like this. This is, no, 0 and 1. I got to have a 1 here somewhere, don't I? Okay. We have to have some sort of mapping here. There is no mapping here. I can supply this. It's me who decides what this x is. It's me who decides what this y is. So in this case, and in all cases, this part is entirely subjective. However, once we specify what the y and the x are, the relation is entirely and always objective. It's just a matter of logic. And let me give you another example. So let me get rid of this. And we don't have a map usually here. My evidence, I want to know whether or not Socrates is mortal. And I could have all men are mortal, all men mortal, and Socrates is a man. In this case, given this evidence that I pick, and this y up here, the probability is 1. It is certain. Given this, it is absolutely true because we have explained to a certain extent y. I haven't explained x. Why is it that all men are mortal? I haven't explained x. I haven't explained why Socrates is a man. Russell has an example, oh, Socrates can be my cat, ho, 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 and we've overthrown this paradigm. We have not, because the grammar, the definitions are all part of this x. They're all in there. We all knew what this means. If you're going to then say Socrates is a cat, ha, 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 okay, Socrates is a cat, then we say nothing about cats being mortal up here unless we have another implicit evidence that Socrates up here is a cat. So you can't play those games. You have to have everything as explicit. All right, and if you're fuzzy about this stuff, you can be absolutely fuzzy about this stuff, but that shows up in this relation. It shows up in this probability relation. So this being the case, we've seen this example of this syllogism many times. Probability is, therefore, the completion of logic. There's no, we don't have to have, you know, I use the example, we do not have to have real things. I could say that all Martians, or half of Martians wear hats. And George is a Martian. And given that evidence there, half of Martians wear hats, and George is a Martian, the probability that y is true given this x is 1/2. Now, obviously, if I change, there's no relative frequency about this. There's no subjectivity about this. Once I have set these things in motion, they become rigorously objective. And the important thing to notice is once I change the evidence, if I change the evidence to 3/4, why then I change the evidence here to 3/4. I change the relation to 3/4. So x can be added to in time. And all I do is I either add to or subtract or both from x, and I have a new x. And if that's the case, maybe I can mark it by a prime or something. The relation stays the same. There are all kind of mathematical tools we develop and so forth that allow us to calculate these things. That's fun and interesting and important, but it doesn't change the interpretation. Okay, so let's look at some other things here. I mean, I can go on and I'm going to have in the written lecture many more examples and so forth, and all throughout the class I've got lots of them. Suppose I have a body of people, I didn't even realize that was a pun. Body of people, they say they drank various amounts, and we have other information like their sex and age, and whether or not they have cancer. And I have a model that relates the amount drank to cancer and their sex and age and whatever else that I want to consider. I have some theoretical model. So this has a whole host of assumptions that go along with it. But all of this other stuff is part of it too. You'll only see usually in the books you crack open, they'll only show you this part of the model. And they'll act like that's the entire equation. They've done the deadly sin of reification. The deadly sin has been committed. It's all of this stuff, and it's all part of this, even though this is the only part that may be mathematized. Now I got a new guy who drinks whatever he drinks, Y amount, and we want to know, oops, that's part of our evidence X. I apologize, my apologies. Oh boy, has cancer, my apologies. A new guy, this is also part of our X, new guy drinks Y. Some small amount y, or x, whatever you want to say, small amount x. So, to reiterate, I got a body of people that I've sampled in some way. They all claim to have drink this amount of whiskey or something, or wine, whatever, in a certain whatever period of time. I got their sex age, whether or not they admit to having cancer or were diagnosed as cancer. And I got a model that relates the numerical parts of these things. And I got a new guy who says he drinks this much, and I want to know the probability he has cancer. It's going to be some p, and that p will be in an interval like this. It probably will not include the endpoints. Perfectly fine thing to do, and a lot in science is comprised of things like this. The important thing about this is once we have this in hand is that there's no decision. No decision. I wish I could have this thing flash on the screen. Probability gives you a number or a word indicating uncertainty, but it doesn't tell you what to do. What's the best thing to do? Now, if this thing is, if p equals 0.8, what's the best thing to do? Doesn't tell you. This does not tell you. Probability does not tell you what's best to do. You may have a decision that also involves uncertainty if you decide to take a new experimental treatment, and that experimental treatment will give so many symptoms, side effects, and pain in its own right, and that kind of a thing. Perhaps that's also uncertainty. Okay, that's uncertainty, and whether or not you'll live if you take the treatment, that's uncertainty too. All that can be handled in the exact same usual way. All uncertainty is, but probability. And probability models don't tell you what to do. Okay, they never tell you what to do. There's no decision inherent in this. Okay, one last one. And that's the example of got job, any counterfactual, tie. I'll just write tie. I'm not going to write the whole thing up. You went to a job interview. You forgot to wear a tie. You didn't get the job. and you were thinking back on it, you looked at all the people in the office as you're thinking back on this as a very formal, old-fashioned office, and you thought to yourself, aha, if I would have worn the tie, I probably would have got the job. So the probability is high. We make counterfactual judgments all the time. We make counterfactual probabilities. There's absolutely no frequency of this kind of a thing. You could talk about historical events. What if what if Lincoln slipped on a log and killed himself when he was a boy, Abraham Lincoln? Would we still have had the Civil War? Well, you can argue that question using this framework, and it's perfectly valid. We all understand what it means, but of course there's no experiment that can ever take place. There's no relative frequency. There's no Bayes about this. Bayes is a mathematical form, but Bayes doesn't tell you what goes into this x and y. And neither is it subjective, because once you give the x and y, it becomes rigorously objective. Okay, that's it. That's the answer. This right here is the answer. Right there. Once we get an x and a y, any, and they go into forming this, and that is all of probability. That's it. Absolutely everything. And it means just what it says. The relation of x, this x, to y. Change any part of x, any part. You got data, you've measured 1,000 people, or you've got a corpus of text that's millions long. You take one out and you put one new in. That's new data. It's a different x. Your probability changes. Probability is not inherent in things. Probability is not part of the world. It doesn't affix itself to anything. Nothing is probabilistic, and that includes even quantum mechanics. We go all over that in class. This is a matter purely of epistemology. If you like, when it's mathematical, it's mathematical epistemology. That's all this is, how we know about our uncertainty. That's it. Okay. That being said, and then of course emphasizing again that probability doesn't make decision. I want to talk about two of the biggest errors that now exist in uncertainty, and an up and coming, very promising error that I think will take over these old ones. The first is testing. And I'm going to write something up on the board here, and you're not going to believe it, and it's not going to make any sense, but we calculate this object, the probability data more extreme than we saw with respect to a model given a belief, a statement, proposition, whatever you want to say, statement about y with respect to a model which says some part of y is false. Okay, you follow all this? And of course, the remaining parts of x are also part of this. This is testing. This thing right here is called the p-value. And it's magical. People would have you believe it transforms usually by one minusing the probability. It's always tacit or implicit. Everybody asks you to believe if this probability is small, the probability of this is high, and vice versa. But of course, it's forbidden to do that in the theory which gives rise to this kind of a statement. It's absolutely forbidden theory to do that. So they never quite say that, and they dance around it. They'll say linked to, associated with, and all of these other words that signal mental difficulties because this bizarre thing is calculated. Again, I'll go through it. You won't believe it, but it's the probability of getting data more extreme than we actually got. We didn't get this data. Nobody's seen this data. We're going to calculate the probability of data we did not see. And not necessarily data, but a statistic with respect to a mathematical function of this model, all conditioned on believing that a certain statement about y is false. So if you have a new drug and you want to test it against an old drug or a placebo or something like this, you'll have a model that represents this, and you'll say, I don't believe there's any difference between these two drugs, the old and the new, or the new and the placebo, or whatever, with respect to a parameter inside of a model. Then you'll calculate a statistic that says, I don't care about the data that I did see, which is over here. Tell me about the probability of data I did not see. And if that's small, then I'm going to ask you to believe that it's tacitly this, but I can't say that. I can't say that because it's not true. There's absolutely no reason in the world to calculate this whatsoever. If we want this, we can calculate this. There's nothing stopping us from calculating this, but people calculate this instead. It boggles the mind. This is a fallacy. This is a formal fallacy. It's a logical fallacy. Some people call it Bernoulli's fallacy. It is committed in innumerable papers over and again, over and again, over and again. You can't talk people out of this because they have discerned the mathematical magic that if this is less than the magic number, then this is certainly true. Or you're supposed to accept that it is true. In fact, it's then a decision. Probability is turned into a decision. I don't know if this is true, you'll say, but I'm going to accept that it is true. It's a decision. Somebody has made the decision for you when they use a p-value. And they don't take into account any of the uncertainty or the loss or suffering or anything else that you would experience or the gains you would experience by knowing directly this probability, which again, everybody could calculate, but they don't. They calculate this bizarre thing. This just won't go away. It just will not go away. And the idea is here, there may be something part of this model that's not actually here, but the part that's false will then be called a cause. So the new drug, compared against the old drug, gives us a probability of data we didn't see as very small. And so we'll say this new drug, and because then we'll reject this null hypothesis that says there's no difference. No difference whatsoever. If there was no difference and we knew that, we never would have done this test, or probably never would have done this test. That's neither here nor there. But when we reject it, we are asked then to believe that there's a cause. No. We already saw with the cancer example before, or I should have emphasized the cancer example before, that when the probability comes out that a person has high probability of having cancer, for instance, say it's 80%. This does not prove that drinking causes cancer. It's a correlation. It is a correlation. This is the big error right here, the big thing. Testing gives the false impression that a cause has been confirmed or discovered. Testing gives the false implication that a cause has been confirmed or discovered. It is an absolute fallacy to say so, a logical, rigorous logical fallacy, but it's done all the time. There's no implication of cause in any of this. If we want to do cause, we have to do brutal hard work. And it's all judged in this same way right here, but where we have knowledge about the cause inside X. I've given the example many times like a chemical experiment. We're going to test for heat added in a reaction. And we control, therefore, absolutely every possible cause or known cause and condition that brings about those causes that cause heat to change. And we're going to manipulate the one new thing, that's our thing, and we have some new chemical or compound or something like this, we're going to add to this test tube, and we're going to check for the heat changed because of it. And it's only on the assumption that we have indeed ruled everything else out. We're going to say, we have indeed ruled everything. It doesn't have to be true, but we're going to assume it's true. And we're going to calculate the probability then. Only then are we allowed to say that we have cause. But notice we start with believing we had cause, okay? And talking about how to confirm models and all that kind of a thing, well, that's something we're going to learn to do. So when is cause really plausible, when is it not, and all that kind of stuff we have to learn how to do. We have not yet done that in the class. We have not gone over this testing in any detail in the class either, and we're going to do it. I can only wish to say that it would end forever. And there's also a Bayesian form of this that I also wish would end forever. Okay. Because again, if we want this, why not just calculate this? The next thing is estimation. And this is where we give a function of a parameter of a model given the old data and maybe a confidence or a credible interval around. This may be some kind of like a mean line or a signal or something like this, a mean line or just a mean number or something like this. In other words, we have a y and an x. We still have our y and an x as always, and we form a model of the relation of the old data is in here, the data is in here, the old sets of little y and little x are all in here and all that kind of stuff. We have a model, and the model will have parameters, little dials, gauges, and so forth, that if we turn them one way, the model does this. If we turn them the other way, the model does that. There's a whole bunch of them usually. We can turn in all sorts of different directions and prove pretty much anything we want. So there'd be a certain parameter in this model related in that same way as that null hypothesis usually, and we'll get out a mean or something. And you'll often see this in time series. Here's time or something like this, and here's some sort of signal y, and the lines will be going like this. The real lines will be going like this. This is the real data, something like this, or in a scatter plot, and the line will go like this. And this becomes that function. And then the deadly sin of reification happens. Everybody believes that this is what really happened. This is the true picture of what really happened. No, the true picture of what really happened are all these dots. This is a model summary of it, which invariably replaces the actual reality. The deadly sin of reification cannot be avoided. And then there may be some plus or minus band around this, but it'll be around this mean. This thing will be called a confidence or a credible interval. In theory, this is different. This is the frequentist and this is the Bayesian version of the two. In theory, they're different. In practice, they're identical. Nobody believes that, in confidence intervals. They'll put it in every book, every frequentist book and everything, and they'll give you a definition at that. At that point, it just leaves the universe. Nobody believes a confidence interval. Absolutely everybody treats them in a Bayesian way. And so if you want the real thing, why not just calculate this? You would have then, if you want an 80% prediction interval by here is your x, it's either time or x or something like this, you'd have a window that looks like this. We could have fuzz in here to kind of indicate all the possible values of y that are possible with a given x. And to replace this picture, this simplistic picture which we're too used to, which leads to vast amounts of overcertainty. And again, claims of cause. Claims of cause. This is a correlation, particularly in time. Becomes a correlation. Okay, that's it. So estimation, we haven't done any of that. We're going to get to it. And the very last error, I'll just write up AI. It's an up and coming error. Actually, what AI does, and it's going to subsume ordinary classical statistics. There's no way statistics is going to keep up, and that's a good thing, because AI does this. AI absolutely does this. They first start with calculating the probability of y given x. They're not reliant on like these old school models and so forth, which over smooth, if you understand what I'm talking about like this. In other words, they lump too many things together, the old statistical models like normal distributions and the like. They just make everything a little too smooth, and sometimes a lot too smooth. AI doesn't do this. And in fact, they search for the great white, which I'll call the great white function, which seeks to tie the function. There's just, once we have a set of data in hand, there's a belief that if we just search hard enough, we'll be able to find the function that perfectly predicts, so that this is either going to be 0 or 1. With this function that's going to be tacitly part of x in here. That function always exists, and it's called, it's a trivial function that says basically just that whatever happened, the probability of whatever happened is 1. And therefore we can always fit our models perfectly. But they don't use that one because that model doesn't predict the future well. So there's this false hope that we're going to find, without identifying cause, a great white function that, like in conformal prediction, it's doing much better than the over smooth methods right now. But then there's the false belief, here's the error now, that once in the end I have come up with a function and therefore I'm going to claim cause. And causal beliefs will be, causal claims will be believed with more strength because they're done by a computer. We can't disbelieve artificial intelligence. That's on a computer. And for some reason, people think artificial intelligence is completely rigorous, forgetting that this is the subjective part, even in artificial intelligence, exactly the same thing. And the second error is the decision. Although AI starts perfectly, properly, correctly with this, it always makes a decision. So I want to draw a cat. You asked, I want to draw a picture of a cat with a machine gun. That's my favorite example. So out will come a cat and a machine gun. And why? Because it knows the causes. What causes does it know? It's got 1 million pictures of cats. It's got 1 million pictures of machine guns. And in those pictures, they're not machine guns. Say, what does it say? Pipe. You know, you draw a picture of a pipe. This is not a pipe. That's not a pipe. The cat is not a cat. The cat picture is not a cat. It's not a cat. So actually, when you're asking to draw a picture of a cat with a machine gun, you're saying, I want a picture. And I know all the causes of pictures because they're just in the pixels. And the danger is not that they're not going to do a good job with that, because they do an excellent job with that. The danger is when we apply this kind of modeling to predicting things like the stock market or whether people have cancer and all these things in hideously complex systems, people are going to believe causal claims out of models because it's done on a computer and it's artificial intelligence. So this error has not yet with us in any full strength, but I predict it's going to come because they're so good at this. They're excellent at this, and that's the goal we had from the beginning. But then they can't help themselves, and they build in a decision. They have to build in a decision for generating pictures. The picture is the decision. But when you decide what to do about predicting somebody has cancer or something, that's entirely different. And the fault will be that you're relying on the prejudices of the coders. And their experience with losses and gains and the decisions that are going to be made may not be yours. You might not share them. All right, so we're going to go through all of that stuff, including quantum mechanics and how to identify good from bad models and how to calculate these probability models and do all that kind of stuff. That is the entire theory, the philosophy of probability, and 32 minutes or something. I meant to get it under 30. I did not because of my rambling mouth, and I still feel like I left a lot out. But if you want it all, it's all there. I got my whole book is online. Jane's book is online. We're only a fraction of the way through these things, and I have already 34 other lessons that you can pick from in some other videos. That's it for now. A full written lecture for everybody will be at wmbriggs.com or wmbriggs.substack.com, and the link will be below there or in my bio if you're on Twitter. Thank you very much for listening.